So in this video, we're going to be looking at three tanks that are in a series, and we're going to be looking at the heights within those tanks. So we're going to be creating a simulation on Google Collaboratory that basically will plot a graph of the heights in each of the tanks with respect to time if the flow rate in is increased. So here's our problem. We are deriving differential equations and simulating the height response of the liquid heights of the three tanks when inlet flow is increased by 20%. We are told that each tank has a cross-sectional area of 1 meter squared and a drain with a 0.01 meter squared big hole. Flow into the system is at an initial steady state, which is 0.1 meters cubed per second, and initial heights of the tanks are equal. So these initial states are very important because we're going to be using solve IVP, which takes an initial value and uses it to solve simultaneous differential equations. And we also have a nice little diagram here on the left. So Q is going to represent the flows. So Qn is the flow into the first tank. Q12 is flow from the first tank to the second tank, and Q23 is the flow from the second tank to the third tank, and lastly we have Q3, which is the flow out of the third tank. We have the three tanks, tank 1, 2, and 3, and then we have the heights, H1, H2, H3, which is the height of the fluid with its respective tank. And so to start deriving these differential equations, we're going to do the very first thing, which is just define what a flow out of a tank is. And so to do this, we're going to use energy balance. And basically what this is the assumption that all potential energy is converted into kinetic energy. And the reason we want this is because we want to take a look at velocity. So potential energy is mass times the gravitational acceleration constant times the height. And kinetic energy is 1/2 mass times velocity squared. And this is the velocity term we want to isolate. And the reason we want to isolate this is because this velocity term is very important when it comes to flow. So what flow can be defined as is velocity times the area that it is flowing out of. And if we take a look at the units, we have meters cubed per second. That's the units for flow. And velocity is meters squared per second. Meters per second. And area is meters squared. And that gives us the units that we're looking for flow. And so to isolate this velocity, we can set the kinetic and potential energy equal to one another, and doing this, the masses will cancel out, so we're left with gravitational constant times height equals 1/2 velocity squared. So isolating velocity, we're going to have velocity equals 2 times the gravitational constant times the height, all under a square root. Now, this velocity for the different tanks, so let's just say Q, the flow from 1 to 2, is going to be the cross-sectional area of the hole times the square root of 2 times the gravitational acceleration times the height. And this is going to be the height of the tank that it comes from. So the flow from tank 1 to tank 2 comes from tank 1. And so this is going to be for all the flows. So Q23 from tank 2 to tank 3 is going to be, but the thing is the height of the area of the drain is the same no matter what. So that makes things a little easier. But the flow from tank 2 to tank 3 comes from the tank 2, so we're going to use the fluid height in tank 2. And then lastly, we have the flow coming out of tank 3, so it's going to also be the drain area times the square root of 2 times the gravitational constant times the height of the fluid in tank 3. And so simplified, this is basically just the flow is going to be the height, or the area of the drain times the cross-sectional area, or times the square root of 2 times the gravitational constant times the height of the previous tank. So let me say that again because I kind of tripped up on my words, but flow is the drain area, the whole of the drain's area, times the square root of 2 times the gravitational constant times the height of the previous tank. And so this is an equation. Technically, these 3 equations are what we'll be using in the code, but this is the simplified version. Now, moving on, we can actually do also not only an energy balance, but we can do a mass balance. So, when we're looking at the change in the fluid height, that's going to be very dependent on the volume. So as volume changes with time, that's going to change the height. And the volume change is represented as the fluid in minus fluid out. And this is just for any tank. That's how it works, is as volume changes with respect to time, it's going to equal what comes in minus what comes out. That's just a mass balance. But the thing is, we are looking at simulating the fluid height, not the volume in each tank. And so we need to break down this volume to have something here and the derivative of the change in height with respect to time. And so how can we break down the change in volume with respect to time to get us something with the change in height with respect to time? Well, it's pretty simple because the change in what we're missing here is the change in volume. We already have the change in height. Well, the change in volume is going to change with respect to height. And we can actually simplify the change in volume with respect to height to just the cross-sectional area. And the reason for this is if we were to look at a graph, that plots the cross-sectional area and the height, this under here, the area, is going to be the volume. So essentially, volume equals the integral of 0 to whatever height of the cross-sectional area with respect to height. And so that's how we can simplify it to the cross-sectional area. And so we have the cross-sectional area equals times the change in height with respect to time is equal to the flow in minus the flow out. So if we were to simplify this, we have the change in height with respect to time is equal to the flow in minus the flow out divided by the cross-sectional area. And so because we have 3 tanks, we're just going to write the 3 equations for each tank. So the change in height of tank 1 with respect to time is going to be the flow in minus the flow from tank 1 to tank 2 divided by the cross-sectional area. And the change in height of the second tank is with respect to time is going to be the flow from tank 1 to tank 2 minus the flow from tank 2 to tank 3 divided by the cross-sectional area. And then the change in height of the third tank with respect to time is going to be the flow from tank 2 to tank 3 minus the flow out of tank 3 divided by the cross-sectional area. So these are the 3 equations alongside of the 3 equations we wrote earlier for the actual flow, which we will just in the code plug in for these values here, the flow 1, 2, flow 2, 3, and flow 3. And now that we have our equations, we can head on over to the code. And so the first thing that we're going to do is just input givens. Actually, to back up a little bit, before we input the givens, we have already imported the packs that we need. And so this first one here, numpy as np, that's a mathematical kind of pack that allows us to do basic mathematical functions. And then we have from plotly.subplots, we import make subplots. This is the pack that we use to graph out the solutions to the solve by VP, and this is what actually shows us the simulation of the fluid height. And then from scipy.integrate, we import solve by VP. So this is the initial value solver that I was talking about that solves simultaneous differential equations. So to start, again, we're going to input our givens. So first thing is just, let's say we import the gravitational constant. That's going to be 9.81 meters squared per second. And then we have the initial flow in. That is going to be 0.01 meters cubed per second. And we have the initial heights, which are all equal. And so the initial height, actually going back, I forgot to write out these equations, but the initial height, we're just going to take from this general flow equation we have. So we have flow equals height of the drain multiplied by the square root of 2 times the gravitational constant times the height of the previous tank. Well, now what we want is we want to actually achieve this height to code. And so kind of reverse isolation, we're going to isolate the h instead. So that's going to give us the flow divided by the whole of the drain times 2 times the gravitational constant squared. Divided by, that's not right. Wrong algebra there. Let's write this out. It's actually going to be the height is equal to the whole of the drain's area squared divided by the flow squared times 2 times the gravitational constant. And this flow, because we want the initial height, we're going to have the initial flow height, or the initial flow rate. So going into the code, the initial height is going to be the cross-sectional area of the drain squared divided by the initial flow squared times 2 times the gravitational constant and so then the area of the drain hole is 0.01. This is meters squared. And I do have to make a correction when looking back at this. The initial flow is 0.1 meters cubed per second. And then we have just to keep everything constant, we have the fact that I think those are all our givens. We do have that the flow in is increased by 20%. So we're going to multiply that by 1.2. So the tops are our givens, and these are our calculated givens technically. Just to keep units, that's going to be meters, and that's going to be meters cubed per second. Okay, so now what we can do is we can derive or define the differential equations functions. So we're going to define basically first the right-hand side of the differential equations. Okay, so the variables in here are the time, and that's what's getting inputted, and then what's getting outputted is the vector. And the vector is basically going to be the different fluid heights. So I guess another input or another given that we forgot to input is the time. So we're going to run the simulation for, let's just say, 10,000 seconds. Okay, so the first thing is the flow in. That's going to be, so we're actually going to move this down here because that's a part of this function down here, which isn't super significant now for the initial code, but when we start doing adding controllers, it has more of an effect. And so now we're just going to code the different flows that we derived. So that's give us the flow from tank 1 to tank 2, the flow from tank 2 to tank 3, and the flow from tank 3. So the flow from tank 1 to tank 2 is going to be the height of the area of the hole times the 2 times gravitational constant times the height of tank 1, and this is all to the 1/2 power because it's in a square root. And then it is the same for all of these, except what changes is the tank that it is coming from. So from flow from 2 to 3 is actually the height of tank 2. We want it to give us the right-hand side. That's what we want the function to return, is the right-hand side. And it's going to return it in an array. And the first one is going to be the flow in minus the flow from tank 1 to tank 2 divided by the cross-sectional area of the tank, which I'm realizing we did not define. So that was given to us, and we were told that it was 1 meter squared. So okay, there we go. And that is tank 1. This is tank 2, so we have to change its flow from 1 to 2, and then flow from tank 2 to tank 3. And then lastly we have tank 3, which is flow from tank 2 to tank 3, and then flow out of tank 3. So now what we need to do, as you can see here, these values are highlighted because they're not defined. We need to unpack it. So height 1, height 2, and height 3 are going to come from the v, which is the vector that we defined. And now what we can do is we can actually do the solve IVP. Basically what it needs is it needs a function. So that's going to be the right-hand side. It needs a time span, so we're going to go from 0 to the time that it ends, which we defined earlier. It needs initial values, so that's going to be the initial heights, and they are the same for all of them, so that makes it pretty easy. And then we need the method, so we're going to use the LSOTA method. It's fairly accurate. Sometimes it can take a little longer, and sometimes it doesn't work for every problem, but it should work for this one. And we are going to say that the dense output, which is like how often it checks it, is true. If we don't, it automatically assumes that it's false. And that's it. That's the solve IVP. We're going to give this a name so we can call back on it later when we go to plot. So we're just going to call this res for resolution. Okay, so now we can start plotting, which is super fun. So we need to create a time plot. So we're gonna do a linearly spaced plot. We're gonna go from 0 to the time end, and we're gonna do 100 intervals. And basically the solutions, so the height of 1, 2, and 3. And the important thing about this is to order it the same. So like when I initially defined it, I put h1, h2, h3 equals v. If I were to put h2, h3, h1 now for whatever reason, it wouldn't be the correct height to the correct tank. And so this is going to be the solve IVP that we defined as res earlier. And we just want the solution, so we're just going to do dot sol, so it's just going to call that specific place. And we need to give it a time, so we want to go for the time plot. And then what we can do is we can make a figure. So we're going to call it fig for figure, and that's going to be make underscore subplots. And we're going to add to that subplot, so it's going to be fig dot add underscore scatter, and the x is going to be the times, the y is going to be the height, so we'll just do the first tank for now, and that's all we'll have for now. And so this is going to be for all the tanks. Oh, excuse me, not going to do that. Okay. Oh, man. The height of the tank. Okay, so now we can shift enter. And we have this beautiful plot here, which is the simulation for this tank. And that is how the heights look after 10,000 seconds. As you can see, they do reach steady state if we were to just zoom in onto this. Oh, let's zoom into this section here. Okay, so looking at this plot, it's not quite right, and going back through the code and figuring out what I did wrong, the first mistake, or the initial mistake here, was in my algebra. When I solved for the initial height, I flipped the flow, so it should be the flow in squared, the initial flow in squared, times the area divided by the area of the hole squared. And if we change that within the code, and then just since we're already back in the code, might as well fix up some other things. Right here, I doubled this for whatever reason. It doesn't, yeah, I'm just gonna fix that. And then now that we're back in here, we might as well clean things up a bit. So we can name this tank 1, and we'll just name all of the lines so we can read the plot a little easier. Take 2, take 3, and if we shift enter, that gives us our plot. So we did also change the timestamp, because earlier, or the time that it was running for, we had it for 10,000 seconds. But you can see it reaches its steady state at like, this is what, maybe 1,000 something, so it doesn't need to run that long. But this is the final simulation with the plot of the 3 tanks in a series.